So in the previous class, we have started discussing about the grid integration. And so our objective is to control the active and reactive power. So that is being injected or that is drawn from the inverter, right? The first thing is, so we have formulated the active power P and the reactive power Q. So these are the original formulas, right? So when the three-phase voltages, the grid voltages are balanced, so under this case, so this VQ will be 0, and so these are the equations for P. So P is so VD into ID, and Q is so VD into IQ. So from this you can calculate the value of ID and you can calculate the value of IQ. So ID is P by VD and IQ is Q by VD. Right. So let us assume that so P star, right? So P star is your reference active power and Q star is your reference reactive power. So these two things, so we are trying to control. So we are trying to control this P star and Q star. P star is your reference active power and Q star is your reference reactive power. So now, so with these two, so how you can extract the reference D axis current and reference Q axis current. So you know that, so P star, so divide this one, so how much? So that gives you this ID star. So what is the value here? What is the value? So what is the value here? So what is the formula for P? So P equal to, so VD into ID, right? So what is P star equal to? So it will be 1 by VD. Agree? So that gives you the D axis reference current. Similarly, so it will be 1 by VD and this is Q star, right? So that gives you IQ star. Understood? Right? So if this Q is 0, right? So this also become 0. This also becomes 0. Yeah. So this is how to obtain the reference D axis and reference Q axis currents. Right. So this is P star is some finite value, right? So these two are, so we are controlling the P and Q. So usually that kind of controls are known as so grid active reactive power control. So these are known as grid active reactive power control. Grid GARPC, so grid active reactive power control. Right. So we have other two things. So one is the VDC reference and Q's reference. Right. So most of the cases, so this will be 0, right? So this is known as VOC, so that is voltage oriented control. That is known as voltage oriented control. As we already discussed that, so there are two ways to control the inverter. So either we will control the grid active and reactive power, or we'll control the DC side voltage and reactive power. So under this case, so this is same, this Q star, this IQ reference, so that is same. So we need to divide this one with 1 by VD, right? So that gives you your IQ star. Right? So whereas, so this is responsible for, so you already know that this is responsible for the Q axis current and this is real power, right? So V star we are maintaining constant, that means we are maintaining a constant, or we are driving a constant load, so which is maintained at a voltage of VDC. So in other words, we are indirectly controlling the active power or indirectly maintaining the active power, right? So therefore, this is responsible for the D-axis current. So therefore, so how to obtain this? So we have the standard one, so that is PI controller. So one side, so this is your VDC star, and this is VDC actual, so plus minus, so VDC star, and this is VDC actual, and after that you have PI controller, so that gives you this ID star. Understood? Understood. Right. So this is how we'll extract the reference D-axis and reference Q-axis currents. So when the reference active, reference reactive power, or the reference DC side voltage, so that is being regulated. So those things are given. Right. Clear? So in this case, right, so we need to measure the actual DC side voltage, and we need to compare this one. And the object with the PI controller is to process this. We have some steady state error, voltage error is there, right? So here this voltage error, so it will turn to 0. So this voltage error is trying to tend to 0 means in that case, so this actual one will follow the reference one. Okay, so that is how PI controllers will work, right? So usually, if it is large system, simply the innermost controller, we may replace with P controller also, right? So, but the accuracy will be more. So when we have this PI controller, all right. So this is how we'll extract this ID star and IQ star. So keep this aside, right? So once these two things are derived, so how to implement the decoupled control? So that we will discuss now. So this grid integration can be done by using two ways. The first one is by measuring grid currents. By measuring grid currents, right? And the second one is so with measuring grid currents, so without measuring grid currents. So overall, so now we are talking about the decoupled control method. So this can be done in two ways. So one is by measuring the grid currents, and other one is so without measuring the grid currents. So remember, for these two techniques, so you need to measure the grid voltages. So grid voltages, so we need to compulsory measure by using sensors, but so we have an option. So either we can measure the grid currents, or we can control by using or by without measuring the grid currents. So usually this will be the direct approach, and this will be the indirect approach. Okay, indirect approach, or this is feed forward approach. So this is feed forward approach. All right. So when you are measuring the grid currents means, so you require additional 3 sensors. So additional 3 current sensors are required. So without means, so there is no sensors are required. Okay. So let us talk with, so without grid currents, so obtaining the decoupled equations or obtaining the inverter control. So without measuring the grid currents. All right. So now, so this is the grid, right? And the inverter is connected through a coupled inductor setup. So this is the setup, right? So we already discussed that. So here this LT and RT, so these are the lumped as coupling inductor parameters. So usually this resistance is very small and it will be neglected. And this is the point of common coupling. And this VABC is the grid voltages, and this VTABC is the inverter voltages, right? And this is the inverter currents. IT, ABC are the inverter currents. Okay. So here, so we either will maintain this VDC, right? So this can be done by using a capacitor. So we'll maintain this one, or else we'll connect a load across this one. So this coupling transformers, we already discussed this. So to match the voltages and to provide the protection, so this coupling transformer will be used. Okay, right. So the first thing is, if you write the differentially, if you write the equation that governing the system, so that will be like this. So between these 2 points, if you write KVL equations, so it will be like this. So VTABC, so meaning is, so it is a 3 by 1 matrix. So it will put in matrix form. So it is VTA, VTB, and VTC. You are aware of this, right? So this entire thing can be written as, so VTABC. All right. So if you write this one, so these are the currents RT into ITABC. So meaning of this ITABC is ITA, ITB, ITC. So this is a 3 by 1 matrix. All right. I think you might have studied when you studied the machine modeling, right? So this LT into DITBC, and this is the grid voltage, so VABC. Understood? Understood, right? So if we convert this into ABC, so this will be the like this, ABC to alpha beta, that is stationary reference frame. So by using Clark transformation, so it will be like this. And so this ABC terms now will become alpha beta 0 terms, and this is the thing. So we transformed into ABC to alpha beta reference frame. So meaning of this one is, so V alpha, V beta, and V0. So this V0 will present, so when if unbalances exist in the grid, right? So this is how we will convert this 3-phase into 2-phase. So next step is, so convert this into DQ, right? So by using synchronous reference frame, so we transform this into this, or else we can directly do this one. Okay. So this is VTDD, right? So this RT into ITD, again this RT into ITD. So in addition to that, so these are the additional things, so that you will get right. You're aware of the matrix, right? So when you're converting this into DQ reference frame, so I hope you are aware of this matrix. So that is RT minus omega L into LAC. That's, you'll get a 2 by 2 matrix, right? So omega LAC into RC. So these are the things. So that is obtained. So this LT into R omega T, and this GT into LT T omega T, right? So if you separate these two terms, right? If you separate these two terms, so it will be like this. Okay. So it is RT into ITD first term plus LT into ITD equal to, so VTD, so this is VTD plus omega LT into ITQ, right? So this is omega into LT ITQ minus VD. I think you are aware of this, right? When you are modeling an induction machine, so here, so you will get the cross-coupled components. So this is RT into ITD, so this LT into VTD, and this one, so this is minus omega LT into ITD minus VD, VQ. So this is D axis and this is q-axis components. So if you notice that, so this one belongs to d-axis, and whereas so this is belongs to d-axis. So that means in d-axis you have a q-axis dependency is there, and q-axis, so we had d-axis dependency is there, right? Okay. So what are these nodes when you're modeling induction machine, right? You might have seen this, right? So what are these things are known as in case of induction machine? You remember that? So how we will represent this in your equivalent circuit? So how you will represent this? You will model the induction machine something like this, right? Okay. So we'll represent this one so with dependent sources. Why we represent with dependent sources means its values are depending on the other circuit, right? And these things are known as, when you model this induction machine, these things are, so we have q-axis components and d-axis equations, and d-axis in case of d-axis equivalent circuit, so we have one voltage that is related to q-axis and vice versa, right? So here, so you are multiplying with some speed, right? This is omega, so that's why these are known as speed voltages. In case of induction motor, so this is known as speed voltages. So here also it is known as speed voltages. So why it is known as speed voltages? So here this is multiplied by the angular speed, and this entire thing that gives you the voltage. Okay, so that's why, so we normally represent it as speed voltages. You might have studied, or you might have heard the term, right? So it is normally represented as a dependent source. So when you model the induction machine in d axis and in q axis. Okay, all right. So this is the one we obtained. So from this, if you want this one only, right? So this is the one. So these two are the inverter voltages. So ultimately you require these two. So ultimately you require these two. So before that, right, before that we already discussed that there are two things, right? So one is with grid control or grid currents, and without grid currents. Okay. So now if you're using without grid control or without grid currents, so here these are the grid currents. So this ITD and ITQ are the grid currents. So we can rewrite these equations. So we can rewrite this equation something like this, right? So you require this ITD, right? By applying this Laplace, so we can convert this, and our object, these two are, see here three terms are there, right? And these three, this one, so this is the first term, so this second term, and this is the third term, so which consists of this IT terms. These are the current related terms. So rest of these two things are, so this VTD minus VD. Okay. So by using these two equations, so we can build some simple circuit, so which uses the Laplace transformation. So the circuit will be something like this. Yeah, this one. So by using these two equations, right, so we can extract the value of this ITD by using the Laplace transformations. Right. So this is how exactly it will be. So here this VTD minus VD. So this entire thing will gives you this plus here. So VTD minus VD. Okay. So here this ITD. So here this output is ITD. So but it's feeding back. Something like this term is ITD into RT. So this is the first term, ITD into RT. Similarly, the second term, so this is Laplace of this one, okay, the Laplace of this one. So that will be 1 by SLT. So 1 by SLT, for LT, it Laplace is 1 by SLT, right? So therefore it is 1 by SLT into ITD. So that forms this term. And similarly, so what is the remaining term? So this is omega LT into ITQ. So you have this ITQ here. So now you multiply it with omega LT, right? And all these terms are added together, right? So this is plus here and this plus here. And so rest of the things are subtracted. This one is, so by using this, so we obtain the differential equation, or we obtain the, if you apply or if you rearrange this one, or if you back calculate this one, so you will get so this equation, right? Similarly here, so for second case, same thing. So VTQ minus VQ here, right? And this is the ITQ current, and it's multiplied by RT here, all right? This also multiplied by, so what you will get here, plus or minus? I think this is minus, right? Agree? Will it be minus here? Okay. So now this is plus here. So now, in the same manner, if you write this one, so this equation you will get. So this one is omega LT into ITD term. So this is omega LT into ITD term. So now you multiplied with this one. So from this, so you obtained the, so from this, you obtained the ITD and ITQ values. Right. So remember, you're not measuring the currents, but you are estimating the currents. You are estimating the currents because you know these two voltages, right? If you know these two voltages, so VABC and VTABC, and you know these two parameters, right? So obviously, by using simple KVL equations, so you can estimate the currents. You can estimate the currents, right? So this is what we done. Okay? So this is what exactly we done. So you know this VTABC inverter side voltages, and you know the grid voltages, and you know the grid resistance and inductance values, that is the coupling parameters. So therefore, so by using simple KVL equations, so we estimated so this currents. All right. Yes.
That omega component comes from the utility grid.
Omega is same for both, right? So this omega term is same for both.
Yes.
Okay, so then only the synchronization will happen. Okay, so you cannot, if it is 60 H, right, or if it is, for example, it is 51 H, or if it is 50 H, you cannot connect the two different voltages.
Yes, sir.
So omega is same for both cases. All right. So once this is done, the thing is that in these things, right, if you remember that we are measuring only the grid voltages. So we are measuring only the grid voltages, and we are anticipated that this inverter voltages are known to you. Okay, so these voltages are known to you. You are anticipated that I know these values. Okay, so that's why it is known as feed forward network. Okay. Someone or some other circuit that gives you these inverter voltages. Some other circuit that gives you these inverter voltages. Right. So in this diagram, so this is known to you. So these things are known to you, right? From this you are calculated this one, and you assumed that so this is known to you, right? But this is obtaining from some other circuit. So where exactly it is obtaining, so now we will discuss. Okay. Right. So if it's a direct approach, right? If it is a direct approach, so that means you are measuring the grid currents. Okay. So in this case, so no need to do all these things. So no need to do all these things. If you measure the grid currents, all these equations, all these things are not required. Straight away, you measure the three-phase currents and convert this into ABC to DQ. So that gives you this ID component and IQ component. Simple. Okay. Right. So no need to measure or no need to do all these things. And moreover, so when you're not measuring the volt currents, right? So here the values are depending on these parameters. So if you accurately know the value of this coupling resistance or this coupling parameter, so then only the accuracy will be maintained. For example, if something is some deviation is there, right? So actual inductance is, for example, 1 millihenry, but somehow you observe that you somewhere you kept that 0.9 millihenry, right? So the difference will affect the grid side currents or affect the inverter currents. Understand? So this thing is entire thing is parameter sensitive. So this thing is entire thing is parameter sensitive. So why it is parameter sensitive? So you must accurately know the data of these coupling parameters. So whenever you have a transformer is there, the transformer leakage inductance is also existed. So all these things you must have a accurate data on that. Clear? So most of the cases, so will not use this one. So nowadays the current sensors are cheaper. So therefore, we normally measure the grid side or the inverter side currents. Okay. So it's just simply convert this into ABC DQ. So that gives you ID and IQ components, right? So there is no headache, nothing. So next we will come to other part. So how exactly this inverter voltages? So once you know the values of ITD and ITQ, right? In the previous one, we discussed two methods, right? So one is without sensing the I2 estimate the value of ITD and ITQ. So without sensing the currents, right? And with sensing currents. So this is without sensing currents, you are obtaining this ITQ and ITD values, right? And this is with sensing currents. So ultimately, so these currents are available in one of the form, either with measuring or without measuring, right? So once you've done this, so next thing is, so we need to identify, so how to remove the decoupling between the D axis and Q axis. If you notice that, so this is exactly what is coupling means. Okay. So here, so when you're controlling this ITD, right? So this ultimately it is controlled here. So that means depending on Q axis. Somehow, so we need to remove this decoupling. So next we have these equations. These are the original equations we obtained, right? So these are the original equations we obtained. Okay. So now this VTD and so this ITD, so these are the inverter voltages. So our ultimate objective is to find out the inverter voltages. Okay. Ultimate our objective is to find the inverter voltages. In other words, these inverter estimated voltages will act as a modulating signals to control the inverter. So inverter, if inverter is there, right? So we need to obtain the modulating signals. So this is modulating signals. That means indirectly, if you know the modulating signals means, so you can control the or you can estimate the inverter voltages, right? So our ultimate objective is to obtain the modulating signal for this inverter. Okay. After that, so once you know the modulating signals, so you can use any of the PWM scheme. Either you can use the sine PWM scheme or else you can use the space vector modulation schemes. That all depends on your choice. But you require a modulating signal such that all these control objectives are achieved. So that means P should maintain its reference value, Q should maintain its reference value, or so that VDC must maintain its reference value, and as long and in addition to that, the source currents, right? So whatever the inverter, so these are the inverter that is drawing some currents, right? So this must be sinusoidal. The inverter current must be sinusoidal. Okay, right? So there is no harmonics in the inverter currents. Right? So if it is a unity power factor operation, so in that case, the inverter currents and the, or in other words, the grid voltage or the inverter currents and the grid voltages in A phase, for example, right? So both must be in phase, so that we can estimate it is operating at unity power factor. In other words, the reactive power is 0. So those things are satisfied. With satisfying all those things, so we need to obtain the modulating signal. Okay, right. So come to here. So how exactly this modulating signals are obtained? So you know the reference value. So this is ITD. Okay. So come here first. So this entire thing, so once you know these values, so there are some standard equations, right? If you remember, so these are the equations. So this is VTD and this is VTQ, so which is equal to, so this is VD, VQ. So these are the inverter voltages or estimated inverter voltages. These are the grid voltages. Okay. Minus of, so this is 0 minus omega LT and this is omega LT 0, right? So here it may be 0 or it may be your RT value. It may be RT. So these are your coupling parameters. So into this ID value and IQ value, I'm keeping all these things in the matrix form, right? So these are some equations are there, right? So these equations I'm putting into a matrix form. Clear? Okay. So in addition to that, our objective is to control the D-axis and Q-axis current, right? So in addition to that, so you require a PI controller so that process the error. So that will be ID star minus ID. Similarly, IQ star minus IQ. So this is multiplied by some K P minus Ki by some time Ts or some time T into integration of this one. This is PI controller, right? Integration of this one. So 0 and you will get, so IQ star minus IQ into dt. So this is the representation of the overall controller, right? So this is the equation, right? And the second part is we need to follow the reference currents, right? So we need to follow the reference current. So ID and IQ must follow the reference currents. So how exactly these are matched? So we can see here. So first we need to control the D-axis currents. So this is the actual D-axis current. So this is the actual D-axis current and this is the reference D-axis current. This will be your reference D-axis current. So how this reference D-axis current is obtained? So how this reference D-axis current is obtained? So here also this is reference Q-axis current and this is the actual Q-axis current. So these things are obtained from this previous slide. Okay, either this one or this one. And whereas this thing, so how this reference D-axis currents, so we already exercised this, right? This is the one. So this is ID star, IQ star. Or if it is a voltage oriented control, so it is your ID star here and this will be your IQ star. Understood? So now the reference 1 or now the actual one is compared with the reference 1 so that the current control is achieved. So that the current control is achieved. So this will be your, and this error is processed in a PI controller here. The objective of the PI controller will reduce the steady state error, right? So reduce the steady state error. So that is giving some component, so which is equal to UCD. So this is the one. Okay, so that gives you this component UCD. Clear? So that means what is the value of UCD, right? So this lies here. So this one, okay. So from this one, so you are that means or space vector modulation. All right. So this is how the decoupled control will present. So this is the overall scheme, right? So this is the overall scheme. The first one, this part, the left hand side part is to calculate the ITD and ITQ values, right? Either you can use current sensors with current sensors or without current sensors, right? So once these things are connected, or we need to connect these two here. So we need to connect these two here. So once these are obtained, so we need to compare with the reference D axis and Q axis currents, and rest of the things, this VTD and so VQ are obtained. Okay, so in the beginning, so when you are estimating the grid voltage or grid currents, so without using the sensor, right? So you require this VTD term and VTQ term, right? So this is feed forward here. So that means, so this is directly connected here. So this point is connected here. Again, so this is connected here. So that's why it is known as feed forward network, and slightly, and it is completely parameter sensitive, right? If you don't want all these things, so directly measure the grid voltage, the grid currents, so and you obtain these things. In that case, this entire thing is not required. Understood? So this is how we will control the active and reactive power, or else we maintain the voltage across the DC side constant. All right. So the overall controller, it will be something like this. Okay. So we have this Q axis. So we have Q reference is there. So this is Q actual, right? So this is the one of the example, or else you can directly use, we already discussed, right? So from this 1 by VD, so that gives you IQ star. So both are same. And this is your voltage VDC, and compared with this actual voltage VDC. This is the actual, this is the grids inverter, right? So this compared in a PI controller, so that you get the value of this ID star. So here you are getting the IQ star here. Okay, and this ID star is compared with the actual ID, right? So how the actual ID is obtained? We have this grid side. So we are measuring the grid voltages. This UA, UBEC are the grid voltages, and so these are the grid currents. IA, IB, IC are the grid currents. So we are converting to ID, IQ form, and this is VD, VQ form, and we used a phase lock loop to obtain this DQ reference transformation. So this provide the theta here for current conversion, and this is for the voltage conversion. All right. Okay. So here, so we are measuring this IDIQ here. So IDIQ, so directly going here. So here your ID here, and this is the actual Q axis and actual D axis current. So this is processed in PI controller, right? And this is the decoupled component. This is the decoupled component which is coming from IQ into omega L minus omega L, and it is coming here, right? Similarly, so this is IQ minus IQ star minus IQ. This error is processed in PI controller, right? And the same control logic is implemented. So everything is same. So only difference is that this is UD, and actually this is VD or VQ. Right. So this is VQ star here, and this is VQ star or VQ HL added. So that gives you, this gives you the modulating signals here. So this is the modulating signal, and by using this PWM scheme, so we can obtain the things. So rest of the thing is the inverter control, right? So after obtaining this VTD, and this is VTQ actually, right? So here the thing is that, so when you're using a sine PWM techniques, the carriers are ranging from +1 to -1, right? So you need to normalize this one. To normalize this one, right? These things are valid from, maybe it's full voltage, right? These are at full voltage, and the carrier comparison is from +1 to -1, right? So we need to normalize this one. So what we have to do is, after obtaining this one, so either we need to divide with VDC voltage or half of the DC voltage, VDC by 2. Okay, so that gives you the normalization. Okay, so that the voltages now are the modulating signals now ranging from +1 to -1 range only. Okay, and another thing is that, so if some noise is present, right, this VTQ value, for example, this VTD, this is the one, right? So VTQ, VTD, right? Sometimes what will happen, some high, for example, this is supposed to be this VTD, so this is D-axis component, right? This is supposed to be straight line. So, but sometimes it will have, what will happen if some disturbance is there or some control reaction is there, so it is producing something like this. Okay. To reduce these high frequency noises, so what we can do is, so we can connect a low pass filter. So after this we connect a low pass filter here. So that low pass filter, what exactly that low pass filter will do, so that will smooth this one, that will remove the only low frequencies are entertained, so rest of the frequencies are removed. Okay. So we'll connect a filter so that the low frequency components only pass through. All the high frequency components are trapped inside the filter. So that is how exactly, so it is working. So in addition to that, what we have to do is, we need to normalize this one by dividing with VDC or VDC by 2, and we need to add an optional low pass filter, so to reduce the, or to smoothen the modulating signal, right? So once this ITD, VTD value are a straight line or the DC component, so rest of the things are sinusoidal, and so we can obtain the output. Okay. So in the next class, I will show you the simulation. So how exactly, so this grid, or how exactly, what we say, these things are achieved. Okay. So any questions? There are questions.